127.4, X is 0.06, and finally we get 0.23 joules is the energy stored in the spring because of this object. And this is how we solve questions of this type. Please remember the formula half kx square, but it is important for us to identify the correct extension value. And how do you find the value of k? By balancing the spring force with mg, because earlier it was given that the object had come to rest. Springs in series and parallel, so we are going to consider them one by one. What is series kind of arrangement? So if there are multiple springs connected to one another, like this orientation, one after the another, this is called a series type of arrangement for springs. Now, in the exam questions, we might have to deal with certain cases where springs are attached like this. So this is a series arrangement. According to the Hooke's law, F is equal to Kx. So there are three important parameters which are dealing with here. Fs stands for the spring force, K is the spring constant, and X is the displacement, which is just how much the spring has been extended or compressed. So for a series arrangement setup, please remember spring force in springs is the same. And why do we assume that? Now, since this is a single string, that is why the total force in this entire string will be the same. This is similar to the concept of tension. If you remember, tension in a rope will stay the same as long as it is one single rope. A similar reasoning works here. So the springs are connected one after another in a straight line. So the spring forces in both the springs will be the same, whereas the extension in the springs will be different. So how much extension happens in a particular spring depends on the value of K. So if you have a heavier spring, that will extend lesser. If a spring is lighter, let's say the value of K is lesser, that will be able to extend a lot more. So to sum up, in series, Fs stays the same, but extension X is different. On the other hand, how does a parallel spring arrangement look like? So if the springs are connected in this fashion, so you can see both the springs are connected to the box. This is called a parallel type of arrangement. Now, there are various types of parallel arrangements which you might encounter in the question. So one is this type, case A. Case B is the vertical orientation of the same. So two springs connected to the same box, but they are vertical. Case C, so the box is connected to both the springs, but one of the spring is connected to one wall, another spring is connected to the another wall. So like in series arrangement, we'll do the same analysis, but the analysis will be reversed. In series, the spring force was the same, extension X was different. In parallel, the reverse will happen. So let's write, in a parallel arrangement, the spring force in the springs will be different, but the extension in the springs will be the same. So like you can see in this image, if there is a box connected to two springs connected in parallel, if we try to push the box to the right hand side, so you can see both the springs are going to be extended by the same amount X. And that is why we say in a parallel arrangement, extension is the same, but the spring force will be different. Because remember, the spring force is K into X. So if X is constant for parallel, the spring force will be directly proportional to K. So stronger the spring, which means higher the value of K, more will be the value of spring force and vice versa. Now, how do we solve questions which involve springs either in series or parallel? There is a concept called equivalent spring constant. Let's discuss that one by one in series and parallel. So a series arrangement looks like this, where the two springs are connected one after another like this. So in this case, we can replace both springs with one spring. That will be the equivalent spring constant. And how do we find that out? There is a formula. So the reciprocal of K equivalent, 1 upon K equivalent, will be equal to 1 upon K1 plus 1 upon K2. This formula we are going to use to solve questions. Whereas in case of parallel arrangement, this is the orientations. So even in this, you can see there are multiple springs out here. So we can replace both springs with just one spring called the equivalent spring constant. But in case of parallel, the formula is different. So the equivalent spring constant is just the sum of K1 and K2. So depending on the type of orientation, whether it is series or parallel, we have to use the different formulas to find the equivalent spring constant. And let's summarize what we have learned so far. Springs in series and in parallel. For a series setup, the spring force is the same, but the extension is different. And this is the formula. For a parallel arrangement, the reverse will happen. So the spring force is different for both the springs, and extension in the spring will be the same. And the formula is just the addition of the two spring constants. So here we have a system that consists of two identical springs connected in series, and the total elastic potential energy is EP when a load is added to both the springs. This is case 1. In case 2, one of the springs is removed and the same load is attached, and we have to figure out the total energy stored in the spring in case number 2. How do we do that? We start with the basic formula for elastic potential energy, which is half into K into X square. Now, in case number 1, where the springs are connected in series, the easiest way to approach such questions is to use the concept of equivalent spring constant, which means even though there are two springs, we can remove them and just put one spring having a spring constant which is called as equivalent spring constant. So the formula for equivalent spring constant in case of series is this. Now, since the springs are identical, let's say the springs are having spring constants k each, since the springs are identical. And now let us write down the formula. We will write down 1 by k equivalent will be equal to 1 upon k plus 1 upon k, which is equal to 2 upon k. And if we take the reciprocal, the equivalent spring constant will come out as k by 2, which means instead of two springs, we can attach just one spring. So let us draw. This is the same situation, case number 1. We are removing both the springs but connecting one spring, which is having a spring constant of k by 2, and then there is a block of, let's say, mass m attached to it. Now, in the question, it was mentioned that the total energy stored is EP. So let's write down the EP will be equal to, now the formula for potential energy is half kx square. But we have figured out the equivalent spring constant is k by 2. So we will write down half into k by 2 multiplied by x square. Now, let's say in case number 1, the extension in the spring is, let's say, x1. So even in the formula, we will write x1. Now, at this stage, since the block is connected to the spring and the block is at rest, we will write that the net force acting on the object is equal to 0. Since it is not moving up and down, it is at rest, so the net force will be 0. After this, let us try to figure out what are the total forces acting on this block. So the first is the weight of the object itself, which is mg acting downwards. And then we have the spring force, which is acting upwards. Why is it acting upwards? Because the spring has been stretched. That is why the spring will try to pull the block up. So spring force and the weight of the object should balance each other. So let's write down Fs will be equal to mg, and the spring force is given by the Hooke's law, which we will write as k by 2 is the spring constant multiplied by x1 is the extension. So this is equal to mg. Now let us make x1 as the subject. So we will write 2 mg by k. And at this stage, let us put the value of x1 in the elastic potential energy expression. So let us write EP will be equal to half multiplied by k by 2 multiplied by 2 mg upon k whole squared. Now, if we simplify this, let's see what do we get. The EP we will come out as m square g square divided by k. Since the 4 will get cancelled out with this 2 square. So this is the total potential energy stored in the springs in case 1. In case 2, one of the springs has been removed, but this spring is also having the same spring constant of k. So now we will do the exact same analysis, but for case number 2, where only one spring is connected. So in this case, let's say the potential energy is EP dash, which we have to figure out. So that will be half k into x squared. In this case, let us assume x2 is the total extension of the spring in case 2. Over here, we apply the same logic that the net force acting on the load or the object is equal to 0, which means the downward weight, which is mg, that has to equate the upward spring force. So let us write down the spring force will be equal to mg, like we did in case 1. Spring force will be k multiplied by x2 according to the Hooke's law, and the weight is the same mg. If I make x2 as the subject, we will write mg upon k. And now we will put this value of x2 in the expression for EP dash. So let's write EP dash will be equal to half multiplied by k multiplied by mg divided by k whole square. And now let's simplify this. The final potential energy in case 2 we will write as m square g square upon 2k. Now, all we need to do is just compare the final potential energy with the initial potential energy, which was m square g square upon k. So, m square g square upon k is EP. So, over here in the expression, what we can do, we can replace the m square g square upon k with EP, which was the original potential energy. Hence, we can write EP dash